Qubits decohere. This is the result of the interactions with the environment. And what's worse, we cannot avoid having these interactions anyway. Indeed, we add noise when we plug external signals into the system, don't we? Thus, the best we can do is to characterize the coherence precisely to understand the time scales at which quantum information can be reliably stored and manipulated. Hey, but wait a moment. Is there a way out there to visualize this decoherence happening? Well, yeah. The power of the quantum behavior relies on interference. This requires relative phases between states. Using a block sphere representation, decoherence can be seen as a movement of the density matrix from pure states on the surface to a mixture of classical states in the inside. Indeed, physicists have identified that decoherence can be described using two different exponential decays and their characteristic timescales. The most basic one is called Amplitude Damping, aka T1 decay, and it simply describes the decay of any excited state towards the ground state on top of the block sphere. This is just another example of nature falling to the minimum of energy, as it always does. Okay, so how can we measure T1? Easy. Just set a qubit in an excited state and track the probability of it staying in that state as time passes. However, the most interesting type of decay is called Transversal Decay, or T2. It happens when the states move towards the center of the block sphere. This is called dephasing, as it erases the quantum phase between states and results in a classical mixture. One approach to measure T2 is to set a state in the equator and track the spiral it follows to the center, as if it were a ball falling down in a sink. Cool, we have it, don't we? There is a problem, but we have to get technical to understand it. To get every time measurement result, we use a bunch of repetitions of the experiment. Then, every qubit we set in the equator might have a slightly different rotation frequency due to small shifts in energy. Each of these frequencies is called detuning. As a result, what we measure, which is the average value of all these qubits, moves to the center much faster. Okay, so how can we fix this? Here it comes the intelligent solution. Watch out. First, set qubits on the equator. Second, let them evolve for some time. Third, this is the magic, apply a pi pulse. 4. Let them evolve for the same time. 5. Observe the echo. Okay, now let me show you what the actual experiment looks like. I'm using Qiskit with the pulse module, which is super cool, because it lets you define your own pulses. So for example, I've used this radio oscillation experiment to define and tune my own pi pulse that takes the shape of a Gaussian envelope with a certain amplitude. And as a proof of concept, if I use the same pulse but with half its amplitude, I can make a pi half pulse. These are my two Lego bricks in the following. So the first step is always to define this pulse schedule or pulse routine, which is simply a timeline of the events that are gonna take place. So in this case, to measure T1, what I firstly make is a flip from 0 to 1 and then I wait some time. And as you can see, I have different routines with different waiting times until the measurement. Moreover, I repeat each of these routines a certain number of shots just to get the statistics of the probability. And I can feed it to get the actual result. To measure this effective T2, I use this other routine, which consists of two pulses. The first one flips 0 to the plus state in the equator, then I let it process for some time, and then I flip it again to measure in the 0-1 basis. What I get now are these damped oscillations, which decay actually pretty fast. This is a result of the qubits spreading through the equator, and this is actually what we want to fix with the Hahn echo. This is where the magic happens, here in the middle. This pi pulse flips the phases and forces the qubits that have spread through the equator to refocus again here, so that we can make a much nicer measurement that shows a clear exponential decay that we can measure. So as a summary, we get these three values for the decoherence times that follow the actual inequalities that we expect from the theory. And well, that's it. The coherence measurements are one of the first things that physicists do when they get their new quantum computers for Christmas. I hope I have shown you the idea behind this process. Thank you!